Assalamu alaikum. Hi students, today is our lecture number 21 for classical mechanics. We are studying chapter number 4 of calculus of variation for classical mechanics. That is the course of BS semester 5th, and the course code of your subject is PHY 509. Previously we discussed about what is Hamilton's calculus of variation. Now we are going to move further. We discussed three definitions for the calculus of variation. Now we're going to move to the next point, that is in which we're going to start from the contents. We're going to discuss about the applications of techniques of calculus of variation. There is first example that is previously continued. We discussed about the shortest distance between the points, and the other is the second example, and in the last we have references. Now moving to the next point. As we are discussing about the applications of techniques of calculus of variation, in this we are going to continue with the first example. The last work we did was the value of C1, that was y dot over 1 plus y dot is equal to C1. We squared the both terms on the right hand side and the left hand side, and rearranging we got C1 square is equal to y dot square over 1 plus y dot square. Then y dot square is equal to C1 square bracket 1 plus y dot square bracket close. Y dot square is equal to C1 square plus, we have multiplied C1 square inside, so we got C1 square plus C1 square into y dot square. Now we're going to take the term C plus C1 square y dot square to the left hand side, that will become minus sign. Then y dot square will be taken common, and then y dot square bracket 1 minus C1 square is inside the bracket is equal to C1 square. Then y dot square taking that term in the division, so we got C1 square divided by 1 minus C1 square. So to remove that square, we'll take the under root on both sides, so that will become here the under root and the square will be cancelled, so here will become y dot is equal to under root C1 square divided by 1 minus C1 square. Now taking this value under root C1 square over 1 minus C1 square equal to a constant C1 C2, then y dot is equal to C2, giving that equation number 8. As we know that y dot is a single differential, and because of the x variable, so we have dy over dx, that is the Euler equations. Dy over dx is equal to C2. Taking the dx from the denominator to the right hand side and integrating, we get integral dy is equal to integral c2 dx. Now after integrating that value, we will get y is equal to c2x plus c3 is the integration constant, giving that equation number 9, which is an equation of straight line. Thus the points P1 and P2 will be on the straight line. So we can write y1 is equal to c2 x1 plus c3. They are the 2 points on the straight line 1 and 2, so we are going to try two line equations. Second point will be y2 is equal to c2 x2 plus c3, and giving that equation, first equation of y1 giving equation A and y2 giving equation number small b. Subtracting these equation, we get, as you know that when we have to subtract these two equations we have to change the sign. So y2 is equal to c2 x2 plus c3 minus y1 is equal to plus minus, plus sign is converted into minus c2 x1, here plus sign is converted into minus c3, then the terms will become y2 minus y1. Here c3 will be cancelled, only c2 will be taken common here, and inside the bracket will be x2 minus x1. So giving that equation number C. From here we took the x2 minus x1 term in the multiplication to the left hand side in the denominator. We got y2 minus y1 over x2 minus x1 is equal to c2. Now considering the equation 1, we have L is equal to integral x1 to x2 bracket 1 plus y dot square whole power 1 by 2 dx. Then L is equal to integral x1 to x2. As you know, y dot was equal to c2, so we wrote here c2. That will become 1 plus c2 square whole power 1 by 2 dx. As that is a constant, so it can be taken out of the integral. So that will be written as L is equal to bracket 1 plus c2 square bracket 1 by 2 and integral x1 to x2 dx, and L is equal to 1 plus c2 square whole power 1 by 2 into x2 minus x1. So from here we get from the previous equation we get that c2 is equal to y2 minus y1 over x2 minus x1. So substituting the value of c2 here, y2 minus y1 over x2 minus x1, putting here we get L is equal to bracket 1 plus bracket y2 minus y1 over x2 minus x1 square bracket 1 by 2 into x2 minus x1, taking the, opening the squares, separating the squares, that will become y2 minus y1 whole square divided by x2 minus x1 whole square, and then taking the LCM, so we have L is equal to bracket x2 minus x1 whole square, and taking the LCM, that here is not the term, so 1 multiplied by x2 minus x1 will give x2 minus x1 whole square plus x2 minus x1 whole square is multiplied by 1, that is 1 plus y2 minus y1 whole square and whole power 1 by 2, and that is x2 minus x1 and multiplied by x2 minus x1. Now we cancel, when then we separate the power 1 by 2 above and below, so we get x2 minus x1 only in the denominator, as 2 and power 1 by 2 are cancelled here. So L is equal to bracket x2 minus x1 whole square plus y2 minus y1 whole square have a whole power of 1 by 2 divided by x2 minus x1 multiplied by x2 minus x1 are cancelled here. So that will give us L is equal to bracket x2 minus x1 whole square plus y2 minus y1 whole square whole power 1 by 2. That equation in the last you can see gives the minimum distance between the 2 points P1 and P2, that are the examples or applications of the calculus variation. Now moving to the next point and example 2. A particle of mass m is projected from origin O with an initial velocity v m projected from the region O, initial velocity v, making an angle alpha with the horizontal. Find the Lagrangian L and determine the path of the particle from the time t is equal to 0 to some other point t such that I is equal to integral t to is equal to 0 to t L dt is minimum. That is also the Euler's equation. Here we have two coordinates x and y. We have a parabolic path of the particle. The particle is projected from the point O origin having mass m, and after projecting it moves with the velocity v and makes a parabolic path and strikes with the ground after some time t, and that velocity that point at certain height has a location or position pxy, and the angle is alpha. Resolving the components of velocity v, we have Ax is equal to v cos alpha and vertical component Vy is equal to V sin alpha. Let at any instant t, the position is given by Pxy. At this point, the kinetic energy will be T is equal to 1 by 2 mx dot square plus 1 by 2 my dot square, because both components are involved of the coordinates x and y. Now the potential energy is given as V is equal to mgy. So the Lagrangian is L is equal to T minus y. We have studied that previously. So putting the value of T and V, in that equation, so L is equal to 1 by 2 mx dot square plus 1 by 2 my dot square minus mgy. As integral I is equal to, at integral t is equal to 0, t is equal to 0 to t, substituting the value of L, 1 by 2 mx dot square plus 1 by 2 my dot square minus mg y dt. Now comparing the integral with the general integral, that is I is equal to integral t is equal to 0 to t f of x y dot, here y is minimum, so f of x y dot will that equation is compared with the above equation. So we have f of x y dot is equal to 1 by 2 mx dot square plus 1 by 2 my dot square minus mgy. In this case time t is independent variable and x y are depend upon the time t. By calculus of variation, if the following conditions are satisfied, number one is d by dt partial into partial f over partial x dot in minus partial f over partial x is equal to 0, and the other is d by dt into partial f over partial y dot minus partial f over partial y is equal to 0. Giving that equation, first equation number 1, and the second equation number 2, comparing the two equations first and previous equation, that is partial f over partial x dot is equal to partial over partial y 1 by 2 mx dot square, that will give 2 by 2 mx dot square. 2 by 2 is cancelled, so we are left with mx dot, and partial f over partial x is 0. So substituting that value in first equation, so we have d by dt into mx dot is equal to mx dot minus 0 is equal to 0, d by dt mx dot is equal to 0. Then integrating that equation, we get mx dot is equal to constant and x dot is equal to constant over m, and then we have x dot is equal to c1. Now by applying the boundary conditions, initial boundary conditions, we have t is equal to 0. So from above equation, x is equal to v cos alpha. So substituting that value in that equation, we get c1 is equal to v cos alpha. Hence x dot is equal to v cos alpha. Here x dot is equal to dx by dt, that is equal to v cos alpha. From here dt is taken to the right hand side, so that will become dx is equal to v cos alpha dt. Integrating both sides, we get integral dx is equal to integral v cos alpha dt, and that gives x is equal to v cos alpha t plus c2. Now t is equal to 0 gives x is equal to 0, so substituting that value, we get 0 is equal to 0 plus c2, then c2 is equal to 0. Substituting in the previous equation, x is equal to v cos alpha t, c2 we get 0 here, so x is equal to v cos alpha t plus 0, and x is equal to v cos alpha t, that gives equation number 3. Now considering equation number 2, partial f over partial y dot is equal to my dot, partial f over partial y is equal to minus mg. From equation 2, we got the value of partial f over partial y dot, that is my dot, and partial over partial y is equal to minus mg. Substituting that values in the equation 2, we get d by dt my dot plus mg is equal to 0. So d by dt my dot plus mg is equal to 0. That gives my double dot, as y dot is differentiable with respect to t, so we get my double dot plus mg is equal to 0, taking the mass constant out of the bracket. So m into y double dot plus g is equal to 0. As we know that mass cannot be 0, so the coefficient of m is equal to 0. So y double dot plus g is equal to 0 gives y double dot is equal to minus g. As we know that y double dot is equal to dy dot over dt, so that will come dy dot over dt is equal to minus g. Now integrating that equation, we get y dot is equal to minus gt plus c3. c3 is a constant. Now to find the value of c3, we have the initial conditions. we put c is equal to 0 and y dot is equal to v sin alpha. So v sin alpha is equal to 0 plus c3. So C3 is equal to V cos sin alpha, and substituting that value in the previous equation in the place of C3 we get Y3 is equal to minus GT plus V sin alpha. So again y dot is equal to dy over dt. So substituting that value over dt minus gt plus v sin alpha and integrating it, taking dt on the right hand side, we get y is equal to gt square with respect to t, gt square minus gt square over 2 plus v sin alpha plus c4. Now again applying the initial conditions, t is equal to 0 and y is equal to 0. When time is 0, the height y is equal to 0. So substituting 0 here, 0 here, we got c4 is and 0 here we got c 0 c4 plus 0 plus 0 is equal to 0. Hence y is equal to minus gt square over 2 plus v sin alpha t plus 0. Y is equal to minus gt square by 2 plus v sin alpha t gives equation number 4. From here we get, from previous equation we get x is equal to v cos alpha into t. So from there t gives is equal to x over v cos alpha, substituting that value here. So we get y is equal to minus into g into x over v cos alpha whole power square divided by 2 plus v sin alpha. So from here that becomes y is equal to minus g by 2 into x square over v cos square alpha plus v sin alpha dot x over v cos alpha. Cancelling v with v, we get y is equal to x tan alpha plus minus gx square over 2v square cos square alpha. This is the equation of parabola. Thus the particle will have a parabolic path. That is the solution of the mass m moving from the point origin O in the two coordinate system xy and attaining a parabolic path and then striking to the ground. Today's lecture is still here. Next will be our lecture continued. Thank you so much. Allah Hafiz. These are some of the references you can follow for the classical mechanics and the lecture we are studying. If there is any difficulty, you can get a reference from here and help. You can ask me your question. If there is any difficulty, we can revise the topic. If there is any kind of difficulty, you can solve the problems regarding the Euler's equation and use them as a sample. Use that lecture as a sample for the solving the problems of Lagrange Euler's equation from the calculus of variation. Thank you so much. Allah Hafiz.